So we had started talking about the 2D experiment with just using the 2-pulse cozy. I don't know if I said that this was the original 2D proposed, just 2 pulses. And to give you a sense of how different the scientific world is now, Jean Genet, who invented this, just gave a talk at a small conference and said, here's a 2-dimensional NMR experiment, and he never published it. And some postdocs who were in attendance of the meeting from Richard Ernst's group went home and said, you can't believe what we just heard. There's a whole new way of doing NMR. And off the field went. Pretty hard to imagine today somebody thinking something up so revolutionary and not immediately publishing it. Anyhow, we figured out that before acquisition, we had 4 operator terms. They were each modulated by some sines and cosines. And the I1 X operator would represent an in-phase absorptive line shape doublet during acquisition. And during the T1 period, it was modulated by the chemical shift of spin 1. So in both dimensions, this term is going to generate a frequency omega 1. So it's going to be on the diagonal. And this term, which resulted from coherence transfer from the second 90-degree pulse, is going to be dispersive and antiphase during acquisition because the operator has a Y transverse component and it has the Z component that tells us it's going to be antiphase. But during T1, it was modulated by the frequency of spin 1. So this is going to be a crossbeat. It's going to be a different frequency in the 2 dimensions. And then the question came up as to what's the fine structure of the lines that we expect. So to do that, we know the fine structure for this is in phase. We know the fine structure here, this is antiphase. We have to work out what the fine structure is that arises from these trigonometric terms. So here, if I take the first one, which was the diagonal term, I can expand this in multiple ways, but one way is to remember the sum and difference trig formulas so that I can write sine omega 1 T1 cosine pi j T1 as 1/2 of the sine of the difference and the sine of the sum. So, I mean, we already see that we're going to get a doublet, right? Because in one case, the frequency is going to be shifted down by pi j, and in the other case, the frequency is shifted up. And then I can write the sine as e to the I as 1/2I e to the I theta minus e to the minus I theta using Euler's law. So I've written that here. 1/2I is the same as minus I over 2. So minus I over 2 times 1/2 is minus I over 4. E to the I omega 1 minus pi j T1 minus e to the minus I omega 1 minus pi j. And then I do the same thing over here. And then I rearrange the terms on the second one. So I have 2 terms that have a positive I and then the frequencies, and 2 terms that have a minus I. And they're inverted relative to each other. That came from the sine. So first of all, we get the antiphase doublet. I'm sorry, we get an in-phase doublet. If I look at the frequencies associated with plus I omega 1, we have a plus sign here. So those two components are going to have the same sign. And then over here, when I have minus I, the two components also have the same sign. So that's in phase, but they're upside down. The two frequency components are upside down, not the couplings. The couplings are both in phase, but the two lines are upside down. So we can then always say that if we see a cosine modulation in T1, that's going to give an in-phase doublet. And of course, a cosine is e to the I theta plus e to the I minus theta. So the two complex exponentials have the same sign. Now, this the sine of omega 1, let's just leave that for a second and ask what the other peak looks like. And that's down here. So the cross peak was sine of the coupling, sine of the frequency. And again, I do the same thing. And now I see if the frequencies are plus I, the sign here is negative. So I have an antiphase doublet. So whenever I see sine modulation with respect to the J coupling, I know the peak shape is going to be antiphase. And again, sine is the difference of two complex exponentials. So I can look and see, again, without actually working out a Fourier transform, whenever I see cosine ijt1, that's going to be an in-phase line, in-phase doublet. And if I see a sine, it's going to be an antiphase doublet. Now there's a problem here that I'm going to get 4 lines. And it's a problem because if I put the carrier in the middle, which is what we usually do, if the RF frequency is set into the middle, then I have a problem that I can't tell a minus frequency from a plus frequency. This is why in acquisition, the receiver has to measure both the X and Y components. In the indirect dimension, we have to measure both the sine component of the frequency and the cosine component of the frequency. That's equivalent to measuring the X and Y projections. But in the experiment, we've only measured one component, the sine component. Everybody clear what the problem is? So here, when I just take this term, this is the term, or say this term was my cross peak. When I just look at what the Fourier transform is going to be of this, I'm going to get 4 signals. There's going to be a signal at omega I, or omega 1 minus pi j, and then an inverted signal at omega 1 plus pi j. Then there's going to be a signal at minus pi j, or minus omega 1 plus pi j, and then inverted at minus omega 1 minus pi. So when I'm looking at my spectrum, if all the peaks have an image plus omega I and minus omega I don't know whether that resonance is really above the carrier or below the carrier. So when I'm trying to match up frequencies, I need to know where the peak really is. Is it 100? Take an amide. If I put the carrier right in the middle, an amide is roughly 4 parts per million downfield. But my calculation here says I'm also going to see a peak 4 parts per million upfield. And that's going to confuse everything because those peaks are all going to appear in the aliphatic part of the spectrum. And similarly, the methyls, which are about 4 parts per million upfield of the water, are all going to have images 4 parts per million downfield of the water. So everything's going to be piled on top of each other in a very confusing way. Now, I could fix this by putting the carrier at the edge. I could put the carrier at 0 parts per million, and then everything would be downfield. And I knew that when I got done with the Fourier transform, everything that was upfield could be thrown away. But that has the problem that then my pulses have to be stronger because they have to cover the full bandwidth, whereas if they're in the middle, they just have to cover half the bandwidth. So that's not much of a problem at 500 megahertz, but it's a big problem at 900 megahertz. Plus, as we'll see shortly, the spectral region that I cover is in the indirect dimension, doesn't matter either dimension, but the indirect dimension is given by 1 over the sampling interval, how much I increment T1 by. So if I put the carrier on the edge and have to cover the whole bandwidth, delta T1 has to be half as small as if I put the carrier in the middle. And that means since I have to acquire a FID for every T1, to get the same maximum value of T1, I need twice as many experiments. If I put the carrier on the edge, the experiment is going to take twice as long. So that's pretty inconvenient. So we need a fix, and this is called frequency discrimination. And we have, so our experiment gave us the sign modulation with the chemical shift. So essentially, we need a second experiment that gives us the cosine modulation. And then we have them both, and then we can put them together. So how do we get the cosine modulation? Well, in this case, it turns out we have to change the phase of either phi1 or phi2. And here, to make it simple, I just changed the phase of phi2. I made the second pulse a y pulse. Here are the 4 terms that we had after the first 90-degree pulse in the T1 period. And now instead of applying an X pulse to everything, I apply a Y pulse to everything. And now we can see which are our observable terms. Right? IZ we never see. So term number 3 goes away. Double and 0 quantum coherence we never see, so this term goes away. Here's the diagonal peak. It is a dispersive signal, and it's in phase during acquisition, but during T1, it's cosine modulated, which is what we want. It's also cosine modulated with respect to the coupling, so that hasn't changed. That was true of our original diagonal peak. And here we have now an absorptive peak that's antiphase. It's cosine modulated with respect to the frequency, which is what we want, and it's still sine modulated with respect to the coupling. So we've acquired signals now that have the cosine modulation rather than the sine modulation with respect to the frequency. I can do my same trick. So here is my original result resolved into, now I just picked out the I minus part of each signal. Here is my new experiment, and I've picked out the I minus parts. And if I add those together, I now see that I have only two lines, both at positive frequencies with respect to the chemical shift. One is cosine modulated and is the diagonal peak because it's I1 minus, I1 T1, and then the antiphase peak that is the cross peak because it's I2 minus, I1 T1. So essentially what's happened is when I had the sine component with respect to the chemical shift, because the sine is the sum of a positive and negative exponential, my mirror image peaks have opposite signs. And when I have the cosine modulation, the mirror image peaks have the same sign. So when I add them together, depending on whether I add them or subtract them, one of the mirror image peaks is going to be negated. And I'll be just left with the other one, with twice the intensity. But of course, I took two experiments, so the noise went up by √2. Now, depending on how this is done, the process might be more complicated. But at the end of the day, one is taking two experiments and adjusting the phase of one or more pulses so that you change after whatever post-acquisition manipulations happen, you end up with one spectrum that is sine modulated with respect to the chemical shifts and one that is cosine modulated with respect to the chemical shifts. And then you turn those into a complex data set. Cosine plus I sine is e to the I theta. Cosine theta plus I sine theta is e to the I theta. And then once we have the exponential, the complex exponential, we only have one line at one frequency. Now, depending on how this gets done, we may end up, depending on how the pulse sequence was written and how our processing program does the calculation, you're doing the first time around. You could get everything wrong and have the wrong component, the wrong mirror image. But usually, you know what the spectrum is supposed to look like. So, for protein, for example, N15 labeled protein, we know the side chain amide groups from azines and glins are somewhere in the upper right corner area. So if they're on the lower right corner, we know we have the other image, the wrong image. So which image we have is just a complex conjugation. So then we just know that we ended up with e to the minus omega 1 T1, how we adjusted the data. And then we just tell the software, take the complex conjugate. Or a carbon spectrum of a protein, the aromatics are down here in the lower left, and the methyls are in the upper right. If it's the other way around, we know we have the complex conjugate and we fix it. If you're doing a 2D experiment for the very first time, some new pulse sequence, etc., it might be confusing as to how you combine your two experiments. And then the safe thing is put the carrier on one edge, run the experiment, and then you know which half you want. And then from then on, you can just put the carrier in the middle. We want carbonyl chemical shifts it's hard to tell which side is up and which side is down because they don't have, any kind of slant to them. They're just kind of a box. And we actually once did deposit a set of carbonyl chemical shifts that were all negative of what they were supposed to be because we had the mirror image and we didn't know it. And somebody pointed out these look a little odd and we had to go fix it. So if you've never done an experiment before, you can always be safe by taking a short experiment with the carrier put so far on the edge, everything is going to be downfield. You can make sure that come out downfield, not upfield when you're done processing. But essentially all NMR experiments have to do this one way or the other. They somehow have to get the sine modulation and the cosine modulation so that they can be put together into a complex number to get a single exponential.
So the way you set this up, I need to take 2 experiments, right?
Mm-hmm.
So even for modern frequency discrimination, like CFCPI and so on, it's 2 experiments for each point that they introduce.
Mm-hmm. Yeah. And
I get only half the digital resolution in the indirect dimension for the same acquisition, right? Evolution duration as in the direct dimension. Like same number of points.
right, because in the acquisition dimension, you take the X and Y components at the same time. So if you wanted the same resolution in both dimensions, if you like, your total time in the indirect dimensions can take twice as long.
Right.
Now, of course, acquiring lots of points in acquisition doesn't matter because that's also, you're waiting for Boltzmann magnetization to recover. That's never the problem. The problem is in the indirect dimension, getting out to a certain value, maximum value of T1 requires more real data collection.
Right.
Now you could say, I started out by saying if I put the carrier on the edge, I have to have the sampling time and then take twice as many points to get to the same resolution. So you could say, well, isn't that the same? Here, I've taken twice as many points because I had to take the X component and the Y component. You could say at some level is really the bandwidth of the pulses, or the real reason that we want to put the carrier in the middle. Not really a time savings so much as the performance of the pulses are better if they're in the middle of the spectrum. And that becomes more and more important as you go to higher and higher field.
And what about an experiment which preserves both pathways?
Right. So then, of course, the problem is here, if we go back and look, we started with a certain amount of magnetization, right? That's the Z magnetization, which would be H bar omega over 2 KT. That's the amount of magnetization we have. We're never going to have more magnetization than that. And now, even if we ignore relaxation losses, we split that into 4. In this experiment, we split it into 4 parts, and 2 of them get thrown away. So on average, we've thrown away half the magnetization. And you'll notice that, for example, this part that is multiple quantum here, actually, I can't see which one it is. This one that's multiple quantum here, this is the antiphase cross peak because this was the Y pulse Actually, let's go back original. So here, this was my antiphase signal, and it's sign modulated with respect to omega 1, sign modulated with respect to coupling. This multiple quantum peak is cosine modulated with respect to the coupling, sign with shift, sign modulated with respect to the coupling. So that's in fact the missing component. If I had that component, I would have both pieces. And in this experiment, this gets thrown away. And that's why we have to run the second experiment. So there are some experiments, and we'll see an example when we get to the HSQC, where both components can be kept. And then disentangled appropriately. So in that case, we gain some signal to noise because you haven't thrown away half the magnetization. That's not every experiment, and sometimes the experiments that recover this other part are longer, so then there's some relaxation issues. But magnetization is precious. So a lot of iterative improvement of pulse sequences these days, when we understand the basic transfer pathways quite well, are aimed at can we squeeze every last bit of magnetization out of the experiment because more sensitivity is critical. Now, absolute phases aren't very important in NMR. It's relative phases that are important. So here, in order to shift the phase with respect to the omega 1 frequency from sine to cosine, we had to shift. I shifted the phase of phi 2 from x to y. But the important part here was that a relative phase difference of 90 degrees shifted the phase of the signal from sine to cosine. So it wouldn't matter whether I shifted the first pulse from x to y and left the second pulse alone. And in some more complicated sequences, it might not be that I need to shift by 90 degrees. There may be some other phase increment. But the only important thing is how I shift the phases around T1 period has to change the sine modulation to a cosine modulation in the T1 dimension. It's more usual to shift phi 1 in this experiment. Most experiments, the pulses before T1 get shifted. There's a paper, I think by Ole Sorensen, that suggests that that's better, that there are fewer artifacts if you shift the phases before T1 rather than the phases after. Theory would say it doesn't matter, only the relative phase shift. But of course, practice on a spectrometer can be different. So you'll notice in the pulse sequence, it's mostly the phases before that get changed. Even though here it was easier to present it as the phases after. So then, once we have frequency discrimination, then we're basically done. We look at the important parts of the sinusoidal terms in T1. First of all, cosine and sine with respect to the coupling are going to give antiphase or in-phase line shapes because the cosine is the sum of two exponentials and the sine is the difference. And then if we went through in more detail here, both of our operator terms have the same modulation with respect to omega 1. So they're going to have the same line shape which we would phase however we want it. More commonly, if we have different modulations with respect to T1, if we have cosine omega T1 in the experiment and some other term that's sine omega 1 T1 omega something, we would say by convention that the cosine modulation is going to be the absorptive line shape and the sine modulation is going to be the dispersive. We just say that because, and again, cosine is 1/2 e to the I omega theta plus e to the minus I omega theta, whereas sine has this 1/2 I, and 1/I is the same as minus I, and minus I is e to the minus I pi/2. So the pi/2 to us is a 90-degree phase shift, which means if x is if cosine is absorptive, sine is going to be dispersive. Of course, when we're done, we can phase the spectrum however we want. But of course, if we change, or we decide we'd rather change the cosine signals to be dispersive, that'll make the sine signals absorptive. But we can't phase them to make them both absorptive. That's just a relative phasing. We can adjust however we want, but we can't do anything about the fact that a term that's cosine modulated with respect to a chemical shift and a term that's sine modulated are going to be 90 degrees out of phase. I mean, of course, people like Fleming Hansen are hard at work on AI programs that would say, you humans may care about, the relative phase. I don't care. You just give me the interferograms and I can figure out what I need to do to give you back in-phase peaks for everything. It's not that it can't be done. It's just that the Fourier transform doesn't do it. The Fourier transform turns them into absorptive and dispersive line shapes. But an AI program can be trained on the FIDs to give you back whatever line shapes you want. Just a matter of somebody sitting down and doing all the training. Fleming, in fact, would say, and has said, that we've designed pulse sequences so they make sense to us and give spectra that we find easy to interpret. Fleming would say in the modern age, we should be designing sequences that are easy for an AI program to turn into spectra we like. And those might not be the same thing. There may be ways of designing NMR experiments that are more convenient for the AI program, even though if we Fourier transform them, they look ugly. So a lot will happen, I think, in the next few years, because it's a simple problem of a spectrum where you have different line shapes. It has been around forever, but it's certainly fixable now. So here's just pictures of the doubly absorptive line shape in the 2D spectrum and the dispersive line shape. And no doubt, everybody who's ever processed a 2D spectrum occasionally gets what's shown on the right there, where you get these ugly positive and negative tails, and you think, I have to rephase everything somehow. So here's just a simulation of the COSY. And it's usual for the COSY to rephase the spectrum so that the cross peaks are absorptive and the diagonals are dispersive. So I did that here. That's the opposite of what the theory said. But again, we can always phase anything by 90 degrees. And now you can see the fine structure. So the fine structure of the cross peaks is antiphase in both dimensions. And we saw that because our trigonometric functions were sine pi j in both dimensions. And then it's harder to see for the dispersive line shape that these are in phase in both dimensions because they were cosine moduli. Now, if we had more coupling partners, these patterns would be more complicated because for every cosine term in the indirect dimension, we're going to get another in-phase splitting. And for every sine component in the indirect dimension, we're going to get another antiphase splitting. So just as you worked out for the operators, where you look at an operator and say, well, first I have the splitting with the big coupling because it was in phase, and then I have the antiphase splitting for the second coupling constant, and so on and forth. We can do the same thing here in the indirect dimension by just analyzing the cosines and sines. And again, starting with the big coupling and working it down. So here's just a cozy spectrum for ubiquitin. And back in the days of this proton-proton NMR, this was always the first spectrum one ran. And for a protein, there's some important characteristic regions, most important. This one, which is the coupling between the amide hydrogen and alpha hydrogen. So a cross peak here comes from an alpha hydrogen during T1, and then coherence transfer through the J coupling to an amide hydrogen during T2. And there should be then one cross peak for every amino acid. So that's a fingerprint. That was the fingerprint region where, knowing your protein sequence, you could count and see, do I have half the number of signals I expect, or do I have twice as many signals as I expect? And you would like to have, of course, there'd be some overlap, but you would like to have the number of signals there that were pretty close to the expected number, telling you we had the sample that was homogeneous, wasn't aggregated, hadn't been something else go wrong during purification. So here is an expansion of that region. You can see the antiphase in both dimensions that we expect. But you can see glycines look much more complicated because glycines have two alpha hydrogens. So there's two couplings, and they may not be the same size. So there's a more complicated line shape. So it's usually pretty easy to pick out the glycines in the cozy. So for example, here for glycine 10, you can see clearly the two couplings. The pattern in test 4 peaks here, so 2 by 2 squares. And here's the chemical shift of one of the alpha hydrogens. There's the chemical shift of the other alpha hydrogen. And they're actually connected to a single amide hydrogen. So in this experiment, pretty easily you figure out which are your glycines. Here are some that are, there's a couple that are just downfield, so they're not on the graph. But here are some missing ones. Why might those be missing? Well, it's notable that the missing ones all have the same frequency, right, in F1 in the indirect one. These are all on this line. And this is about 4.7 parts per million. That's water. So this experiment was run with pre-saturation of the water, and it bleached the alpha hydrogens. It saturated not only the water, but the alpha hydrogens that are under the water. So to find these, one has to do some other experiments. And there's variants of the experiment where the water isn't saturated, so then one can find these. Not so important these days. Perhaps. I mean, this one isn't, well, this one is interesting. We're going to see in a couple of minutes, again, that the spectral region that one samples is given by 1 over the increment in T1. That's also true in T2. But resolution is set by the maximum value of T1. And that's because if you have two sinusoids that are very close in frequency, you have to observe a very long time before you see a phase difference between them. Discriminating frequencies is basically discriminating relative phase. So if the frequencies are far apart from each other, they acquire a relative phase very quickly. But if they're close, right, they're in synchrony for a long time until they build up a substantial phase difference. So if you want to resolve two peaks that are close in frequency, you have to observe a long time, basically the reciprocal of the frequency difference. So you can see that here. Here are 3 different posies with different values of the maximum in the T1 dimension. So here the maximum is relatively short. I don't remember the number. Here's intermediate, and here's a larger value. And you can see the improvement in resolution as one gets to longer values of T1. Yep.
Both for this and for like the N50 based spectroscopy, what would you do if your protein had a lot of proline?
So obviously you don't see the prolines in this fingerprint region, and you would then use a different set of experiments in order to find the prolines, but you would have to be using one of the aliphatic hydrogens. The alphas are betas, gammas, deltas as your readout, which have the problem of being more congested. And same thing in the N15 HSQC, we don't see the prolines. If you want to see the prolines, you would do something like HCAN, where you relay from the alpha hydrogen to the alpha carbon, and then to the proline nitrogen, and then back again. So, yes. So there's a lot of sequences deposited where people have just done the backbone without the prolines, and they're just not in, not in the data set. So why not always just collect a very large maximum value of T1? If high resolution is good, why not just always collect very high resolution data? Why would that matter? And why is the signal weaker? So why does it decay?
Relaxation.
So relaxation. So first of all, of course, even in the absence of relaxation, you are usually undersampling what you could in T1 just because it takes a long time. Right? Adding, doubling the number of T1 points doubles the length of the experiment. I mean, you can double the number of points in T2 for free because that's your recycle delay, or part of your cycle delay. But in T1, to double the number of points means collecting twice as many free induction decays. The experiment takes twice as long. And then beyond that, even if you could afford the time, you then have the problem of relaxation. You obviously, there's no point to be collecting data once it's decayed into the noise, because then you're not gaining anything. So in fact, one usually in the T1 dimension is only sampling to the T1 max is roughly equal to the T2 or maybe 1.5 times T2 of the protein. So that the signal is decayed, but it hasn't decayed towards a very small signal that you're trying to measure above points. Get past this for a while. Yep.
What is then the overall benefit of sampling non-uniformly?
So in if we're going to do a Fourier transform, we have to sample every point. Actually, let's go to the sampling numbers once. Let me go down the line. In here somewhere. Here. So for Fourier transform, we have to sample an integer number of sampling delays. If the sampling delay is delta t, we have to sample, let's say, 0 times delta t, 1 times delta t, 2 times delta t. If we don't do that, then suppose we take we leave out every third point. That would mean what we've done is taken the real signal and multiplied it by a function that is 1 for every first and second point, 0 for the third point, 1 for points 4 and 5, 0 for 6, so on and so forth. And then what's called the convolution theorem says that the Fourier transform of that signal, the product of a real signal and the sampling function, is going to be the convolution in the frequency domain of the Fourier transform of our signal and the Fourier transform of the sampling function, this thing going between 0 and 1. And the Fourier transform of this thing going from 0 to 1 in some pattern is going to be something with a lot of sidebands going on and on. If we just had a step function, the Fourier transform of step is a sinc function, which has a central band and then a bunch of oscillations. So something that's a bunch of steps is going to be some complicated pattern of peaks and ripples, so that our line shape in the Fourier dimension is going to be very highly distorted when we do that. But spectrometers have gotten to be very sensitive. So we may have enough. So suppose we want to sample to high resolution. That's going to take a lot of time if we have to sample every point. But maybe the spectrometer is sensitive enough that we have more than enough signal if we were able to sample only 10% of the points. And then the problem is, what do we do to reconstruct an NMR spectrum if we haven't collected every point? We can't do a Fourier transform, or we can't do a Fourier transform and not do anything else to try to reduce all the artifacts. So algorithms have been developed that then allow you to calculate a spectrum that is more or less artifact free from an undersampled grid. And there's many programs now that will do this. Mostly, there's different ways of doing it, different mathematical ways of doing it. But it can work, really remarkably well. In a 4D experiment, sampling to high resolution, would take you a gigantic amount of time because you have 3 indirect dimensions. But some of these non-uniform samplings, you need 10% or less of the actual grid points to get a high quality spectrum out. So Shabani, for example, would say, you're running 3 or 4Ds, you probably should never bother collecting full grid. You should collect a fraction of the grid and use the time savings to sample the larger T1 maxes. So, for example, if we just did a 2D nitrogen 15 HSQC on the protein, we might take 256 complex points in T1. But then if we were going to do an HSQC nosy 3D, conventional way of doing it, we might only take 32 complex points in the nitrogen dimension. So you sacrifice a huge amount of resolution in order that the experiment not be so long, and then hope that the expansion into the cube gives you enough resolution to offset the fact that your resolution in the nitrogen dimension is low. But with non-uniform sampling methods, you're not making that compromise anymore. I could still sample out to the same value of T1 max that I was doing with 256 points, but I just don't have the 256 points. I have 32 points scattered in that array. So, but then I think these algorithms, as have been, a huge effort was put into developing these algorithms for non-Fourier reconstruction. And I suspect they're all going to be rendered obsolete by AI programs, which, again, if they're trained on a training set, then they won't really care what the sampling schedule is. I mean, you have to pick a sampling schedule and train on the sampling schedule. But I think, again, this is an area where it's really clear AI is going to be brought to bear in a big way over the next couple of years. Yep.
Do you exactly know hydrogen? You're not just like scrapped it out of what it.
It's a funny thing. The answer seems to be no. And it's peculiar that a number of the algorithms for doing the reconstruction don't actually know the sampling schedule. The sampling schedule might be designed so that you know that it's going to minimize artifacts. There's good sampling schedules and bad sampling schedules, and people have invested a lot trying to figure out what a quote unquote good sampling schedule looks like. But when you actually come to reconstructing the spectra, many of the algorithms don't need to know the sampling schedule. And you would think it would work much better if they knew the sampling schedule, but somehow usually no. Peculiar. Whereas I think when it comes to training AI probably is going to need to know the sampling schedule. I think it'd be very hard to train an AI program that can be fed a spectrum sample with a sampling schedule it was not trained, that the AI program wasn't trained on. Well, it'll be interesting to see how this develops. But it always has struck me that it seems like it must be helpful to know the sampling schedule. But whenever I ask the people who actually work on these things, they say, yeah, not so much. So this is what's called the Nyquist frequency. 1 over twice the delay. But of course, since we sample positive frequencies and negative frequencies because we're doing quadrature, then we can sample from minus Fn to plus Fn. So our full spectral width is 1 over delta T. And that's a calculation, you have to do all the time when you're studying how wide your spectral width is in a 2D experiment. And on a Brooker, that's invariably IN0. And that's something you set, or you tell the spectrometer the spectral width you want, and it'll calculate IN0 for you. And perhaps not so critical. Where does this come from? This basically comes from the fact that if you want to tell the frequency of a sinusoid, you need to sample at least 2 points per cycle. And 1 point per cycle isn't enough to estimate the frequency of the sinusoid, but 2 points per cycle is enough. I don't know that I can prove that. That's so this is our frequency range. If we're sampling at delta T, then the frequency range is minus Fn to plus Fn, or the total spectral width is 1 over delta T. Now what happens if we have signals outside that range? And it will turn out that they appear within the range that we've sampled. And that's called folding or aliasing. Aliasing is easiest to see what it might mean from English. They have the wrong frequency. They're supposed to be somewhere over here, but they've appeared in our spectral region. Now, this you could see as a disaster for NMR, because during acquisition, suppose I have on a 500, 10 parts per million spectral width for hydrogen. That's what I set my spectral width to, so I'm sampling appropriately. Well, that is 5,000 hertz. The noise goes on forever. White noise and signal at every frequency. So all of that noise would alias back into my 5,000 hertz range. So I would pile an infinite amount of noise on top of my spectra, and there'd be nothing. So to fix this, the spectrometer has to have filters in it that filter out frequencies outside of a certain range to prevent this catastrophe. And in the old days, the filter technology was extremely important because the filters were built from, analog electronic devices, and they have a certain bandwidth and then some roll off. There's amplitude distortions, phase distortions. But now those filters are actually set pretty broadly, so they don't impact your spectrum at all. And then after acquisition, a digital filter, which can be much better behaved, is applied to the data before the Fourier transform, kill off noise outside of your defined spectral region. That noise problem is only in the acquisition dimension. It doesn't apply in the indirect dimension, because that's not real frequencies or real data. But folding happens. So here's a simple example. So there's the example of sampling a sinusoid. The solid line samples the sinusoid at 2 points per period. And then you can see the dashed line is a higher frequency, but it goes exactly through the same sampling points. So if I only have those 4 sampling points, I can't tell the solid line apart from the dashed line. They look exactly the same to me. If I want to distinguish them, I have to take more sampling points, which means a shorter delta T, which opens up the spectral region. So now the dashed line appears where it's supposed to be. So here's an example. I have 3 signals, square, circle, and triangle. And now I have a small value of delta T, a large spectral width in the vertical dimension, and I see all 3 peaks where they belong. Now the other 2 cases are folding and aliasing. And in the literature, these tend to be used interchangeably. I try to use folding to mean the case where the edges, the top and bottom of the indirect dimension, look like mirrors so that you reflect. So this peak ends up getting reflected across this boundary when I narrow the spectral width. This one gets reflected down. And then when I call aliasing, the edges, the top and bottom of the spectrum are connected like a barrel, like a cylinder. So then you just keep wrapping around the cylinder. So something that's too high at the top is going to reappear at the bottom. And something that's at the bottom is going to reappear at the top. Now, the way these days, it used to be kind of split, but these days, most of the time, the way we acquire the spectra, this has to do with the way frequency discrimination is done. Most of the way the frequency discrimination is done these days, you have this situation, that the spectrum looks like the top and bottom are connected in the cylinder. So something that's off the top wraps around to the bottom, something that's off the bottom wraps around to the top. We tend to do it this way because, again, sometimes this is useful. So a carbon spectrum, as I said, the aromatics, they're down here, the methyls are here, the aliphatics are here. If we want to resolve the whole spectral width, we need a very small value of delta T. But we can make delta T larger and let folding put the aromatics here and the methyls here, but they're still out of the way of the aliphatics. So as long as we don't pile peaks on top of each other, folding can be to our advantage in indirect dimensions because delta T can be larger. So we can get to a larger T1 max with a smaller number of experiments. So we speed things up by folding. So because of this, data isn't acquired this way so often. But you can just remember, there is another way where the edges look like mirrors doing this. And as I said, I try to reserve folding for the edges are mirrors and aliasing or the edges are a cylinder. But in the literature, people use same words for both. I had a little impact how this works. Now, as long as we're in this section of the notes, we might as well say that there's another huge impact on the fact that we actually do a discrete Fourier transform. You know, the theory says we have a continuous signal, we do a continuous Fourier transform, but in reality, we're digitizing the signal in acquisition, or we're digitizing it in the indirect dimension because we increment delta t in discrete amounts. And you might think it doesn't matter, but actually it matters a lot. So here's our signal. There's what a Fourier transform looks like. So on and so forth. But here is the discrete Fourier transform. So now it's a sum, not an integral. And the first consequence you can see is this is periodic. The continuous Fourier transform isn't periodic, but the discrete Fourier transform is periodic. And that had a lot of consequences. Now, this series can be summed for our signal. Our signal is going to be sinusoids decaying with some exponential rate constant. So for that special signal, this can be summed. And here's the line shape. And the question is that the same as this line shape? A continuous Fourier transform, we get the absorptive part and then the dispersive part in a complex signal, a decay constant here, and maybe a phase shift. So is this the same as that? And it's not obvious that they're the same, but it turns out that they're the same for two circumstances. One, if the initial sampling point is 0, and we multiply the first point of the free induction decay by a factor of 1/2, or the first time point is set to delta t over 2 at the sampling interval, and we apply 180-degree first order phase correction, because during that time period, the signal is all going to evolve. And if you've done 2D experiments, you probably have recognized that almost all processing programs have a parameter that you set to be either 0 or 1/2. And you either need a first order phase correction in the indirect dimension, or you need 180 phase correction. Back before this was recognized, I mean, I was a postdoc when people figured this out. So this wasn't known for a long time in two-dimensional NMR. You would end up with, just depending on what the initial delay was, you would end up with some arbitrary first order phase and some possible streaks in the NMR spectrum that you just kind of lived with. Streaks obviously are bad for quantification, but First order phase corrections aren't benign either because they lead to baseline distortions, except for special values, and the special values are multiples of 180 degrees. So this became very important in getting the best possible base planes into the experiment, which is very critical in experiments where you're trying to quantify weak peaks. And it almost always turns out, no matter what you do in NMR, eventually the weakest peaks become the most important peaks. So having the best possible base plane is super important. There's another aspect of this that comes from the periodicity. And I don't know where it is in the notes, so I'll say it and eventually we'll come to it. The fact that the signal is periodic is the reason why you have to Fourier transform by a factor of 2, or should Fourier transform by a factor of 2. Zero fill by a factor of 2 before you Fourier transform. If you zero fill by more than a factor of 2, you're essentially interpolating between data points. So it's perfectly fine to interpolate, but interpolation isn't new information. That's just interpolation. But a factor of 2, zero filling, is real increase in information. It comes from the fact that the signal is periodic and causal. There's no signal before we start sampling. So the signal only exists once we start sampling. It's zero before that. So the combination of those two factors mean that you should always zero fill by a factor of 2. This is a consequence of something called the Kramer's-Kronig relationship, and I'll upload a paper that's a nice outline. One way of thinking about this is, suppose we have n complex points. So in the indirect dimension, we've acquired n cosine modulated data points, n sine modulated data points. We put them together to make a complex number. We have 2n data points that are independent of each other, and that are cosine modulated and that are sine modulated. When we do the Fourier transform, we're going to get back n complex frequency domain points. N of them are the absorptive spectrum, and n of them are the dispersive spectrum. But we don't normally look at the dispersive spectrum. We look at the absorptive spectrum. So there's something wrong. We started out with 2n independent data points, but now we're only looking at n data points after we do the Fourier transform. The Fourier transform is a linear operator, so the information content is the same before or after the Fourier transform. So by looking only at the absorptive part, we've thrown away half of the information available to us, which doesn't seem like a good thing. And a consequence of this Kramer's-Kronig relationship is that if we have periodic causal signals, and if we zero fill by a factor of 2, so that after the Fourier transform, we end up with 2n points in the real, 2n points in the imaginary, the Kramer's-Kronig relationship says, now the real and imaginary are related by a, what's the transform called? Starts with an H. Hilbert transform. Anyhow, there's a mathematical transform that turns the real data into the imaginary data. So if that's true, now the real data must have all the information, must have all the 2n information, and the dispersive part is now dependent on the real part. So that regains all the information into the absorptive line shape. You know, this is probably somewhere in the course notes, but I'll upload this nice explanation of the Hilbert transfer. Kramer's-Kronig relation. How are we on time? Any questions online? So we started to talk about this as part of the problem set. That if we have our product operators in the shift basis set, we can count them up by their coherence order. We can label them +2 means we have an I plus and an S plus. And +1 would mean, say, I plus or S plus or I plus SZ or IZ S plus. So they're not a complete orthonormal basis set because there's some ambiguity. +1 can be assigned to a number of coherents, not unique. But we certainly can do that. Now the question is, suppose we have such a coherence with some coherence order, what happens if we change the phase of a pulse? And the answer is shown here. If we change the phase of a pulse, so that we've had, just like the problem set, you have some starting operator and some destination operator. And then we want to know, and we have a pulse that converts the two. And now we change the phase of the pulse. What happens to our answer? And it's shown here that if we start with a coherence order, say P sub I, and end up with an operator that's P sub F for initial and final, then delta P is P final minus P initial. And if we change the phase of the pulse, our final coherence will change, will acquire a phase change of minus delta P times 5. So it's a very simple result. All that changing the phase of the pulse does is change the accrued phase of our final operator. And that accrued phase is simply the change in coherence order times minus the phase shift. So we actually worked this out on the board. Over here, it's still on the board. We worked it out last week. It's worked out again in the notes. Here's the same proof that I did over there. So we get the same result, maybe with a minus sign error somewhere over on the board, since I think this is right. So if we change the phase, our destination coherence changes its phase by minus delta P times 5. A very simple result in this basis where we're using the pluses and minus operators. But this means, for example, if we apply a pulse to some set of operators, we could end up with a number of different values of delta P, depending on what the destination operators were. So that means if we shift the phase, our final operators might acquire different phases relative to each other. And that's the basis of phase cycling, in which we want the receiver to follow the phase of our desired coherence and hope that leads to destructive interference of the operators we're not interested in. So what does the receiver have to do? So if we shift the phase of a pulse, we want to shift the phase of the receiver to compensate for that phase shift. So we shift the phase of the receiver, that's also a Z rotation. And then we end up with the fact that if we change the phase of our pulse, our coherences change their phase. And then there's a contribution from the receiver. And what I would like to do then is sum up over some shift of the phases so that here the phase shift depends on where I am in the sum. And my hope is that for a given value of delta P, I can make this sum go to unity. And for other values of delta P, it'll go to 0. So, a simple case, suppose I have a Z operator and I minus operator, and the Z operator obviously is independent of the phase shift, and the IX operator depends on the phase shift. So when I shift the phase of pulse, I'm going to vary the phase of the IX term, and I'm going to shift the receiver. And if I shift the receiver, for example, from, suppose I take the change of the phase of the X operator from plus X to minus X, and I change the receiver from plus X to minus X, then the signals are going to add, but the Z knows nothing about the change in phase. So the Z terms are going to cancel. So even if later on that Z term gets turned into something that's observable, it's still going to be canceled because half the time the receiver is going to be positive and half the time the receiver is going to be negative. Now, most of what we do these days, this is pretty simple because when you're doing heteronuclear experiments, mostly you're taking the heteronucleus from say IZ to I minus or I plus and then back to IZ. There are so many experiments, although they exist, where you're generating say double quantum nitrogen magnetization. So if you're just taking things between Z and plus or minus 1, then mostly you just need 180-degree phase shifts of the pulses and 180-degree phase shifts of the receiver. But when you have multiple quantum coherences, this becomes more complicated. There are just some pictures to illustrate that if we change, suppose we start with Z magnetization, so that's coherence order 0, I apply a 90-degree pulse, I'm going to get coherence orders -1 and +1, and now I change the phase of the pulse. But if I leave the receiver alone, the dot is the receiver. When I put the magnetization on X, or on an X pulse, picture isn't so great. How do I label it? So picture isn't great. That should be the minus Y axis, obviously. I have the receiver with the magnetization. Then I change the phase to Y. The magnetization is on X. The receiver is still on -Y. Here the pulse goes to Y. The magnetization, or pulse goes to -X. The magnetization goes to Y. The receiver stays the same, and now the pulse goes to minus Y, the magnetization is on minus X. And I have absorptive, dispersive, minus absorptive, minus dispersive, and the four signals add up to 0. So if I want the signals to accumulate, then every time I change, or the same thing would happen if I changed the receiver phase. If I left the pulse the same and changed the receiver phase, I would see the same thing. And if I want the signals to add up, when I change the phase of the pulse, I have to change the phase of the receiver to follow the signal I care about. And then all four signals add up. So that's the basic idea. And then if we do the detailed analysis of this, which we're not going to do, we would have two rules. And there's periodicity here, so that if our phase cycle has n steps, for example, if n is 4, then I'm taking 90-degree steps to go around the circle. If we have n steps, periodicity means we're going to pick out a change in coherence order of delta p plus multiples of that, where the multiples are some integer times capital N number of steps. So, for example, if I want to select a delta p of 1, and I have 4 steps in the phase cycle, I'm going to also detect a delta p of 5 and a delta p of -3 and -7 and +9. Now, it's pretty hard to generate +9 coherence order changes, so those may be irrelevant to me. But -3 is certainly going to be, could come up quite easily. And within this range, since this is periodic in n, that means I could arrange things to pick out delta p of 1, and then I would have -3 and +5. Or I could arrange to pick out delta p of 2, in which case I would have -2 and +6, or 3, in which case I would have -1 and +7 as the other ones. So which one I pick out, which value of delta p I pick out, depends on how I shift the receiver. So if I have n steps in the phase cycle, there's kind of n unique delta p's plus all the images. And which delta p I pick out is determined by how I shift the receiver. And the other ones are guaranteed to go to 0. In this case, all the other ones are guaranteed to sum to 0, except for the ones that are the aliasing by plus or minus n or plus or minus 2n. So for example, suppose quite frequently, I might want to keep 2 coherence order pathways, say +2 and -2. So if I want to keep them, they have to be aliases of each other. They differ by 4, so I need a 4-step phase cycle. So that if I select -2 by how I shift the receiver phase, I'm also going to get +2 for free. And this just has detail. For example, if this was an unwanted pathway, that's a coherence order change of -1. And this is going to be suppressed when I do this phase cycle. So that, in a the nice thing about the theory is that I haven't proven, I just told you, is this is guaranteed. If you have an n-step phase cycle and pick out one value of delta P by how you shift the receiver, then everything else is going to be canceled except the images. And frequently the images you might arrange because you want one of the images, like keeping plus and -2, or the images might be such high coherence orders that you're unlikely to see them. I mean, to get a coherence order of 5, we're going to need 5 coupled spins. And that's not so likely. There are some famous ones, so exercycle, for example. We would like 180-degree pulse to take +1 to -1 and -1 to +1. That would be a perfect 180. So that's a coherence order change of +2 or -2. So a 4-step phase cycle will do it. So the phase cycle is 90-degree steps. What does the receiver have to be? I go back to my rule. My rule is the receiver has to change by 360 degrees divided by n times delta P. So n is 4. I got n had to be 4 because I wanted to keep the coherence order change of plus or -2. And I want delta P of 2, so the receiver phase shift has to be -180 degrees. -180 and +180 are the same. So the receiver goes to the phase goes x, y minus x minus y, and exercycle. X, y minus x minus y, and every time we do a 90-degree phase shift, the receiver changes by 180 degrees. And then we will pick out coherence order change of plus or -2. Now, that might seem overkill. What would happen if I just use a 2-step phase cycle? So here in the 4-step phase cycle, if I pick a coherence order of 2, the 4-step phase cycle says I'm going to suppress everything except -2 and +6, and +6 I don't care. A 2-step phase cycle, if I select +2, I'm also going to select 0 and -2. So that wouldn't be as selective as I wanted. Some artifact in the 180 would come through. And that's these diagrams are called coherence level diagrams. Just to show what's happening, the coherence as it goes deeper. So for example, if I started with Z magnetization, I would start at coherence order 0, a 90-degree pulse. IX magnetization is I plus I minus. IY magnetization is I plus minus I minus. So both a 90-degree pulse splits everything into plus or minus 1. And then here the 180 would interconvert them, and so forth. The main downside to this is phase cycles can become very long. If I have a sequence with even 3 or 4 pulses, and each pulse needs a phase cycle of 4, and they all have to be done independently, before long, you have 64-step phase cycles, and the experiments become enormously long. So in the old days, when spectrometers were very insensitive, this wasn't so important. You had quite a ton of scans anyhow. But these days, spectrometers are very sensitive. You don't need so many scans to acquire a FID. So one needs to shorten the phase cycle. Unfortunately, radiance, which we'll talk about next time, can do, for example, radiance can do this in 1 scan rather than 4 scans. So we can replace exercycle, the traditional way of phase cycling 180-degree pulses, with a gradient deco and reduce by a factor of 4 for every 180-degree pulse that we think we would need to clean up an artifact. If you've looked at a modern pulse sequence, they're littered with gradients everywhere. They're largely replacing what would have been done by phase cycling before in order to make the sequences take less time. And because of this periodicity, if you don't acquire the full phase cycle, if you say, I need 4 steps, but I'm only going to do half of them, then there's likely to be artifacts. Sometimes you can get away with it if the artifacts aren't large, but a consequence of this periodicity also means that you really need to do them all. All right, so let's take a 5-minute break and then go over some of the problems in problem set 2.
Twenty-eight steps in the phase cycle is still a reality for solid then.
Okay, so there you have to figure out a cogwheel phase cycle for shorten.
Cogwheel.
Yes. So Malcolm Levitt had some papers. We have one paper on it. There's the notion, if you imagine your phase cycles as being gears with different numbers of teeth, is there a way of having the phase cycles vary in a correlated way rather than independently? That also will get selection, but with fewer total steps.
I will look that up.
Now, I don't know in practice how, I mean, it's a very clever idea. And Malcolm gave a couple of examples in his papers for solid state NMR. I don't know how much they've been used in practice. I'm very happy with our paper.
proving one aspect of how they work, may use blanking on the first thing, the coin problem. So the coin problem is, suppose you have a denomination of coins where there's only 2 coins and they're relatively prime. So those are 5 cents and 3 cents are your only coins. What's the largest number of change that you can't make? Obviously, you can make 6, you can make 10, 8, 15. What's the largest that's impossible to make?
Well, it's actually bounded.
Pardon?
The largest is bounded, it's not an infinite.
Right. Once you're above a certain number, you can make everything. Well, it turns out the answer is the product minus the sum.
And then,
Everything larger than 7 can be made in that case.
oh,
Bizarrely, that was proven in the 1800s, and we used that paper in our paper. Bizarrely, the answer is not known for a set of 3 coins.
oh,
So
unsolved.
5, 3, 5, and 7. There's not a proof of what the upper bound is. There is one. There are theorems that put bounds on what the upper bound would be. There's no proof of an exact formula for more than 2. It's related to the chicken McNugget problem. For a while, the different boxes of chicken McNuggets were relatively prime to each other. And some mathematician having lunch with his son figured out what number of chicken McNuggets can you not buy by buying an integer number of boxes and wrote a paper about it. So we're going to do some of the problems that hopefully you've already done and sent in. I'm probably just going to do 2 of them right now, just because they're very illuminating. So since you've all tried to do the problems, what is this one? I should probably look at my keys, so I'll make sure I know. What was the suggestion? $180x
Yes.
and Any other possibilities?
So 180, why would I say it?
So any 180 will work. And then we can always say that I alpha then I have I z plus e. So any 180 is just going to have minus I z. And that's I. That's good. Remember, 180 always turns out fitting to be. So the toughest one is the problem set. I1 minus I2 minus I1 minus I2z. And the best thing to do first is to use this to figure out what we want to face. If if we had, let's assume we're going to work out some answer for X phase. And then we want to know what happens if we shift the phase from X. So in that case, over here, we have the initial equals -2. And over here, we find that is -1. Delta P is -1 minus 2 is +1. We find out minus P initial. So if we start and work the problem out for X phase, and then say we're going to change the phase, whatever our answer was is going from doing the pulse for X to doing it for 5. We're going to acquire a phase of minus I 5 times +1. We can work the problem out for X and then figure out, looking at that answer, trying to figure out what phi should. So then we have to work the problem out for X. So I did it by saying I1 minus is I1x minus I times I1y I2x minus I1 I2y. And I'm applying beta X pulse. So when I do that, I'm going to get a bunch of terms. Now, whatever beta X is, it's not going to affect this. And at the end, I only care about the part that depends on I2Z. So beta X acting here, the only part I'm eventually going to care about is going to be minus I, and then X takes Y to plus Z. With a component sine beta. there's other terms. There is the IX term, and here there would also be I2Y cosine beta. But none of those are in my desired destination, so I can drop them. And now over here, when I apply the beta X pulse, nothing happens here. I1X stays the same. And again, part of this goes to the Z-axis, but that's never going to be part of I1 minus. So I don't need to worry about that. All I care about then is part which is minus I cosine beta I1y. I have to turn this back into I minus. I minus, again, is IX minus IIY. The part that's on Z isn't important. So I simplify my life by throwing away a bunch of terms that I know I don't need. Yeah.
Why do you not care about the IC?
There isn't. This would generate an I2Y cosine beta. And then Z sine beta. And then IX is a half I minus plus I plus. I don't care about the I plus part because I'm trying to get back to I minus. And then here I have minus I cosine beta. And then IY is 1 over 2I plus minus I beta. And I only care about the I minus I plus minus I minus. So I only care about the minus I1 minus part. And over here I have the minus UZ and beta. And just as I've gone along, throwing away all the terms I don't care about, just to make my life easier. So this here, I have, this I isn't supposed to be. I1 is 1 over 2I plus minus I minus. So these two i's cancel. I can bring out a half I minus 1 plus cosine beta. And over here, I have a minus I sine beta I2Z. So there's my two operator terms. That's what I wanted to get back. And then here's the amplitude factor. Now, this is a phase. Minus I can write this then as 1 plus cosine beta times a half e to the minus I pi over 2 I1 minus I2Z. Now, I want to shift the phase of the pulse so that I cancel this phase. And then I'll just have a real number times my desired operator. So what should phi be when I now change the phase from beta x to beta phi? I'm going to acquire a term minus I over two minus I5. So I want to make this pi over, I want to make this term to be pi over two. So phi needs to be minus pi over two, which is a minus y plus. So I did the calculation for x. I knew from this theorem what would happen if I changed the phase from x to phi. And I used that phi dependence to cancel any phase shift that resulted from my calculation using the x plus. Any questions about this on the line? It's kind of hard. Hopefully you can see.
Look at that.
Pardon?
Look at that.
The computer seems like it's run out of battery. Hold on. Sorry about online people. Let me get the computer hopefully started up again. Yeah. Zoom. Let me get back into the Zoom. Let's see any better. Pardon?
It's looking from the computer scan.
I think. Anish, can you grab the brush? Sorry, online people. It was working. Well, my computer lost power,
Oh,
and then when we come back, we don't see that.
okay, this thing is rebooting. I don't know how, I think even this lost power.
Well, my computer lost power because it wasn't plugged in there.
Yeah, this is rebooting. Does it show up now?
No, it's somehow looking as usual.
Yes, in the, when you do the share, and
Yeah,
You don't see second catalyst?
Is this second camera?
Yes.
Oh, I click on it.
Maybe that might like to clear, sometimes better if you unplug and put it back. I think one more time, if you stop sharing first and then start sharing. So it's not shared, if you look at that, share this part.
Yeah.
Stop it and start it. Still looking at it.
Let me go back. Does that work?
Yeah.
So it's going.
Power cycle is maybe.
We should be seeing something here. Should I just try sharing?
Yes. No, it goes back.
Find the second camera.
This is not anything I see. Serious. No.
Should I try exiting Zoom?
No, that will stop. No, you can. Yes, that's right there.
There we go.
Okay. Focus it a little bit.
Sorry, online people. So just to revisit,
our rule about phase shifts of coherence orders told us that if we shift the phase by phi, we'll accumulate a phase shift of e to the minus I phi. And then that let us work the problem out for an X phase pulse. And I threw away as I went along all the terms I knew I wasn't going to need. You may have kept them all because, of course, doing it the first time, you don't know what it is you need to keep. And I ended up then with my desired term plus some imaginary constants, which I remember as an NMR person are phase shifts, and then some grid terms that depended on beta. So now, if I change the phase of the pulse, I'm going to acquire a new phase shift, e to the minus I phi. And I want that phase shift to cancel the phase shift that came from my calculation with the X phase pulse. And then looking at this, I see that phi has to be minus pi over 2, but I have minus pi over 2 plus pi over 2 equals 0. And minus pi over 2 means a minus y phase pulse. So I, of course, having done that calculation, could see if that's true. Let me erase what I did and say, let me just start with a minus y pulse. So a minus y pulse leaves this alone and is going to turn Ix into some z operator that I don't care about. And then I1x cosine beta is the part that stays on the x-axis. So I have I1x cosine beta minus Iy. All this stuff that we have. And now the beta y pulse is going to leave this alone, and I don't care about that. And it's going to rotate some of the x up to z. And a minus y is x to plus z. So I'll have plus Iz sine beta there. And now when I do what I did before, I1x is a half I minus plus I plus that I don't care about, cosine beta. And Iy is 1 over 2I minus I minus, minus I, 1 over 2I minus I minus, Iz sine beta. So that is I2z. So a half I1 minus, I's cancel, minuses cancel, 1 plus cosine beta, sine beta, I2z. And that's the answer with all the phases canceled, which is what we wanted to do. So I1 minus looks like the right thing. And now I just have a function that I want to maximize f of x equals 1/2, 1 plus cosine beta, sine beta. I just maximize that by taking the derivative and setting it equal to 0, or asking ChatGPT how to maximize that function or Mathematica, whatever. And I found the beta, I think is 60 degrees. Does that sound right? I got beta is 60 degrees. And then f of x came out to be 0.65. So that I can transfer 65% of the coherence from the first operator to the second, and 35 ends up in all these terms I threw away. I think if you go over this problem and understand it, it tells you pretty much everything you need to know about pulses and phases of pulses. The next one after this is similar, except that you can probably intuit the phase by looking at the operators. And then the one that is I1, X, I2Z, I3 alpha, going to minus I1Z, I2Y, I3 alpha. Actually, looking at my answer, I think I answered. Interesting. I'll have to fix the key before I send it to you. Uh, I don't think so, because a beta Y applied to I2Z won't generate I2Y. Well, let's try to fix it. Maybe somebody has a right answer. Anybody want to tell me what phase they got?
I don't think I'm right, but I had a basic I with four wrong. It's always in the order plus x but minus y minus x plus y minus y.
Okay. Two, I1, X, I2Z, I3 alpha, and we might as well write this right away. To I1 X, I2Z, times E plus I to I1 X I2 Z I3 Z. And then, well, the suggestion is we need a beta pulse that's phase shifted by 45 degrees. And here's X, Y, Z. We want to do so in our recipe, we should rotate everything backwards by pi/4, and then apply the beta pulse, and then rotate everything forwards by pi. So if we rotate by -pi/4, this becomes 2 I1X minus I1Y plus, and the 2IZ is unaffected. I2Z plus 2 root 2 I1X I2Z I3Z. And now, yep,
It's supposed to be a factor of 2 on the right,
to
like on the position of it.
here,
Yeah, on the right side, we have factor of 2.
yes. I3 alpha is IZ plus a half E. This is
Half is the whole half.
our, I need another half.
Yeah. No,
No,
it's just the half outside.
Yeah.
Half of IV plus.
A half IZ.
No.
Yeah, 26.
Yeah, but you do have half IV plus half E.
Yeah.
Yes.
Yes.
So I think I need IZ plus 1/2 E. Because IZ is a half I alpha minus I beta.
Okay.
So this is right. This, you have another a half. This should be a half E here, so that should cancel this.
Oh, so there shouldn't be the factor of 2 on the left now, right?
Yeah, I took it out here.
Okay.
And then we apply the beta X pulse. So we have root 2 over 2 IX stays alone. IY become, there's a Z part, which we don't care about for our destination operator. So, oh, we care only about the Z part. So X takes Y plus Z. So it's minus I1Z. Find data. We don't care about the X part in the destination. And then the X pulse takes I2Z to I2Y sine beta with a minus sign. And then over here, we have √2. And again, we want only the Z part, so minus I1Z sine beta. And here, we only want, we want the Y part here, so again, minus I2Y sine beta. But here we want to keep the Z, so we need the cosine. I3Z cosine beta. Now, when we multiply these all out, we're not going to have any i's, any imaginary terms. We'll have possibly some minus terms. Now, the answer wants a minus here. I think, yes. So let's count minus terms. So here, there's 2 minus terms. So we're going to get something that looks positive, and the answer wants something that's negative. So the way to get something negative, if we have a positive number, is to multiply by a phase shift of 180 degrees. Because e to the I at 180 is -1. So that suggests that maybe we need a minus pi. You said plus pi over 4? Well, we have to undo the rotation. Maybe it's too early to say. Because now we have to undo the 45 and minus 45. So you have to multiply everything by pi over 2, pi over 4. Rotation.
The I2Y, negative I2Y becomes positive I2X. Right. And then it is only
Yeah.
one negative sign in both terms.
And I was too quick to drop terms because this I1X is going to rotate to be some I.
Yeah.
You only want to see
Yeah, I think
Here.
it's fine. I think, yeah, it's fine.
this. This one is fine. Only Z. This will be. I guess we're okay. So then we have to rotate everything again by a positive 45 degrees and keep only the right terms. So √2 over 2. these two minus signs cancel. I1Z, sine beta, I2Y. And that's what we want. When we rotate, this is gonna get another factor of √2/2.
What the X?
I think we want only the Y component.
Yeah, I think we have in ours, yeah, we have 2x, I have 2x, I2y.
Like, I follow in what I think the problem is. That could be. I think I solved the wrong problem. So this is going to rotate to
This is 6.
the minus x to x. Over here. Another √2/2, which will cancel. This goes to these two minus signs cancel again. √2/2 minus x, it's like a minus sign here. I won't include. Where the cosine beta I see. And then.
Or can I kick you out?
Oh, yes, and anyhow. Looks like we'll have the minus signs, and that's fine, and then we just have to convert this back to alpha. By making substituting in a half I alpha minus I beta, and remembering over here, we have to substitute in I alpha plus I beta. For spin 3, left out the alpha terms, and then do the calculus to find the maximum. I'll try to redo it because it looks like I made a number of mistakes. Sorry for online people, we lost you for a while. I'll try to turn